we will let Maurice continue with his second part of the talk. Thanks.
Yeah, okay, great. So, so now I'll come to the second part, which are also the most recent results. So I should also mention that this is a joint with Benjamin Fahs and with Fahs and Kozhan from last year, where we try to apply these ideas for multiple orthogonal polynomial ensembles. So these two theorems in tandem, they are not yet enough. You actually have to put some more input in it, like the Denisov-Rachmanov theorem that I mentioned before, or some other kind of inputs here. And for multiple orthogonal polynomials, actually the story becomes a bit more complicated, but therefore also interesting. And that's what I want to discuss now. So now I guess that not many of you are familiar with the concept of multiple orthogonal polynomials, let alone multiple orthogonal polynomial ensembles. But I think that most of you have seen some models that actually are multiple orthogonal polynomial ensembles without them being called like that. So before I come to a definition, let me first recall an example of a model that does like that. So this would be an example of non-colliding Brownian bridges that have, for example, one starting point. They all start here at 0. They start at 1 point, but then they have 2 points that they can go to. So we basically have n, or let me call it capital N non-colliding bridges, Brownian bridges, and let's say that we have capital N of them, and N1 and one of them and two of them end up somewhere else. And here there's an endpoint A1, and here there's an endpoint A2, and they are different. Okay. And if you would cut this model somewhere halfway, you would look at these points here, then the distribution of those points are a bi-orthogonal ensemble, but that's actually an example of a multiple orthogonal polynomial ensemble. So typically when you have like non-intersecting paths that have like one starting point or densely packed starting point and two endpoints or two groups of densely packed points, then you actually have multiple orthogonal polynomials. So another example would be, if you look at the example of the hexagon, but you would cut out, oh, I have to draw it correctly here. You would cut out some parts like that, maybe like this. The fact that you cut out a piece and you have basically two groups where you could end also gives like it gives also multiple orthogonal polynomial ensembles. So this model would also be part of that, of this what I'm going to talk about now. Okay, so what you want to study, of course, in these models is that you take an n that goes to infinity, but also we want an n1 and n2, both of them, that they go to some nu j, which is an element in 0 to 1. So both n1 and n2 go also simultaneously to 0 and scale with n in a linear way. And that's important also. Okay, so that's basically what you would like to understand in these things, the large n limit. So let me then say what is a multiple orthogonal polynomial ensemble. So that's a little bit more general now. There is quite a few things that you have to say here. So first is that what you have to assume is that you're given an m, which is a natural number, and this is the number of different endpoints. So in this case, is m equals 2. Okay, so there is a number of different endpoints, and then we also have different weights. So we have wn x to wm of x, and these are, let's say, the all weights, and let's say also everything happens here on R. It's not really so important, but we have weights on R. And then we also have these multiplicities, how many go to A1 and how many go to A2 and so on. So this will be collected in a vector. So this is an N1, 2, and Nm. And we take the length of this vector is just the sum of the entries to Nm. This is capital N. Okay. So this is basically just the weights they correspond to the different endpoints. These N1 to Nm are sort of the multiplicities of these, right? And then you consider an MOPE. So that's just that's like a joint probability distribution on x1 to points xn of the form. Well, then there is a determinant of xj to the k minus 1. This is just a fundamental determinant that we usually have, but now we don't square it. It's also normalizing constant. But there is a second part that is a bit complicated. jxk, where j and k run from 1 to n. And these functions, I also will just put it now on the Lebesgue measure to make things slightly simpler. Oops, what happened here? dxn. These functions here, so this gj, they are linearly independent and taken from the span now of w1 of x times w1 of x, and then I multiply this all the way through to x to the n1 minus 1 times w1 of x, and then I start with my w2 of x, go to x w2 of x, and so on and so on, x to the n2 minus 1 to the w to the x, and then I start with my w3, and so on until I'm done. Okay, so I have n1 of those here. Here I have n1 functions. Here I have n2 functions, right? The next one has n3 functions. So in the end, I have n functions there. And I take gj just linearly independent from this span, and I compute this determinant. Okay. So instead of just having two fundamental determinants, I have a slightly different matrix here, the determinant of G. It has also polynomials inside, but also these weights. Okay. And if you would, for example, look in this case here, maybe I can say in this case, you would, for example, have, now that's not exactly correct, so, but I might have some constants wrong, but the wj here would be an e to the minus x squared over 2 plus, let's call it cj of x here. And the c would depend on a1 and the time t and so on and so on. So with some appropriate scaling, these are just some shifted Gaussians here. Okay. Okay, so this is a rather particular definition, but actually it appears quite a lot. You can also get it from Schur polynomials. So there is actually an interest in studying such ensembles also from a general perspective. Now, before I come to these sort of matrices, now the recursion, the matrices G, things get a little bit more complicated in multiple orthogonal polynomials. So let me first give a definition of so these are some definitions that that I will have to go through. It's like a multiple, so an MOP, and this is called type 2. They're also type 1, but that's maybe they don't, let's a little bit put them in the background. They play a role, but let's put them a little in the background. So these are just polynomials that have an index n, but actually in this case, it's a vector of indices. So actually, I want to call it k. So it's a vector of k, and k here is in this n to the m. So k basically has components k1 to km. Okay, and pk is a monic polynomial. So it's a monic polynomial of degree k. The length of this is k1 to km, and it satisfies the following condition. The k of x is x to the j minus 1 WLx dx. This integral will be 0 for j running from 0, oops, not j minus 1, just x to the j, j to kj minus 1, and not j, L, right? So for each WL, it has to be orthogonal. There's an orthogonality relation with the x to the j, and j runs from 0 to kl minus 1. So these are these indices. And then we have actually this for all weights. L is 1 to m. Okay? So there is a bunch of linear relations here on the coefficients of the monic polynomial. And you may hope it's not a theorem and it doesn't have to be true, but we will assume here to be true that this defines the polynomial uniquely. Okay, so that's basically also a little bit of an assumption here. It's called what's what we call a perfect system. But okay, I want to just put that also into the background. It's not so important at this time. So these are polynomials that behave very much like orthogonal polynomials, but they have a slightly different structure. So one of the things that is important for us is that they also have recurrences. There are recurrences for these polynomials. But these recurrences, they are a little bit less nice and well, maybe they are nice, but they are a little bit ambiguous, actually, I should say. For these polynomials. So what you can do is if you multiply x p k of x, well, this is a pk of x is a monic polynomial of degree k, right? So you get a new polynomial of the higher degree. The degree is 1 higher. But actually, which one is it? Well, it's a k plus 1, but there are actually quite a few candidates to get a polynomial of a degree 1 higher. You could, for example, say I take the pk, and I add a ej here. Like, well, these are the canonical factors. So ej is just the canonical factor that has zeros everywhere, but at the jth location a 1. So I can add higher the degree in m different ways. Okay, well, okay, but you can show them that you can do this. This is fine. Then I can multiply this with a pk of x, and actually I can express this into this sum. Let me call this L. And here there is coefficients AL, K, P, K minus EL. So this is like it's no longer a 3-term recurrence, but it's like it's a relation between a polynomial of a certain degree and then, well, the polynomial of degree higher plus all the polynomials of degree 1 lower, right? So this is a complicated thing that you see. Now I should also say, this is A here. These coefficients that you see here, AK, they do not really depend on which J you chose here. They're always the same, okay? So these A here, they only depend on K here, but not on what I chose here. So this actually gives some sort of consistency that X of PK, is that if I would look at the difference of pk plus ej, but now I subtract the pk plus el, for example, then I just, well, if I just, from this relation that I wrote above, I can just see that this is going to be equal to the L k minus the bj of k times the pk of x here. That's just the left-hand side. So these are consistency relations. So there's all kinds of relations here. And from these consistency relations, you could actually build also different recurrences. You can play around. There is a whole set of equations that you can play with. So maybe this is actually, I always think it's easier to see this if I put this a little bit graphically. If I just take m equals 2, then you can see this more clearly. There is a grid here. And for each, okay, this is a very bad grid, but you get what I mean. So for each sort of point in my grid, it gives me a polynomial, right? And polynomials that are on the same line here, slanted line here, have the same degree, but they are different. And this nearest neighbor recurrence basically says that if I have a polynomial that's sitting here and I multiply it with x, then there is a relation with this polynomial, and then I can choose this one or that one. Right? I can choose, or I can choose both. I can also take the average of the two relations. But I can choose. And this consistency relation basically says that if I look at, now let me draw one more. This consistency basically says that if I have these two polynomials together, the difference of them can be expressed into this polynomial as a linear combination of this. Okay. So there's all these sort of relations between these polynomials. So the recurrences become much more complicated. Okay, so there is actually people never speak about the recurrence relation for these orthogonal polynomials. There could be many different ones. But the nearest neighbor recurrences, they have a special role. And actually, what you can prove, or well, actually, this is not really a proof. There is some special class of multiple orthogonal polynomials that we are particularly interested in, and that is what we call the Devie class. So this is you have a Devie class for orthogonal polynomials, but you also have a Devie class for multiple orthogonal polynomials. And it is a class that is a class where these coefficients have limits. Okay, and this is, we say, so the weights here, W1 to Wm, are in the Devie class. If the limits of these coefficients, I had b coefficients, bj, k, if there is sort of limit for those, let me call them bj and then a nu, and a limit here of the aj, k, and this is going to be aj of nu. And the limit is when k goes to infinity, but this vector k over k goes to a nu. So this is a nu1 to nu-m, which is a vector in 0, 1 to m, right? So what I'm saying is,
Maurice, a quick question. Is there any a priori condition on W1 to Wm to guarantee that you're in the Devie class?
So this is actually something that is currently under investigation, actually, and there is some papers by Aptekerov and Denisov, I believe, that they actually proved this, that there isn't such a condition. There is there are conditions on the weights where you have where this condition is satisfied, yes. But I think that there is still some work to be done there, but that's very recent, yeah.
Okay.
That's in the last few years, and also I think Ross also has worked on this problem also. So there is this is an ongoing, and actually maybe your motivation for studying this is the following theorem, actually, because if you are in the Devie class, then you have a central limit theorem. So then you can apply this machinery from theorem A and B that I said, and the result is then the theorem is that if you look at x of f, which is of course a linear statistic, and this is under the condition, wait, I should say. So if W1 to Wm are in the Devie class, then E minus xf, this here converges to a normally distributed random variable where you get again x to fk, f minus k, but these are not the Fourier coefficients now. Fk is going to be 1 over 2 pi times the f of z plus sum over aj nu of z minus bj nu. So this now, instead of It's sort of a rational function here. J is 1 to m. And here is dz over z to the k plus 1. And this is the theorem by myself and Benjamin Ross. Actually, this is one theorem. We actually have some other theorems too. You also include varying measures. Then you can also do something similar. But I didn't want to complicate things there further. So if you have these limits for these recurrence coefficients, which are expected to be quite common, and there are theorems right now, then you actually have a central limit theorem. And the difference is that you actually, instead of, usually before we got a az plus b plus a over z. This was from the unitary ensembles. When you have a one-cut case, you have a central limit theorem, and these a's and b's are basically related to the endpoints of the interval. Here you get something different. You get something more complicated. You get a rational function as the symbol, basically. Okay, and the way you prove it, I want to say a few words in the remaining time on how you prove this, right? So this is a slightly more complicated problem than just for orthogonal polynomials for the reason also that why this is actually a more complicated one is this set of weights in the Navai class is a more complicated problem than in the scalar situation, because you can, in the scalar situation with orthogonal polynomials, you can go to the Jacobi operators. There is some spectral theorem, a spectral theory, and so on for self-adjoint or symmetric operators. But in the multiple orthogonal polynomials, the recurrence matrices are actually not even so easy to define. There is no symmetric or self-adjoint Jacobi operator. So that makes the problem actually a little bit more complicated, right? So, and this also makes it complicated for us to prove this theorem. And I want to show you a little bit, because there is quite a nice structure behind it that I want to highlight a little bit in the remaining time. Okay, so let me come to the overview of the proof then. So the thing what you need to do is to show that, I mean, the multiple orthogonal polynomial ensembles, they're also bi-orthogonal ensembles, but you have to actually, there is an ambiguity in defining it as a bi-orthogonal ensemble using these orthogonal polynomial and multiple orthogonal polynomials.
Sorry, just a quick question.
Yeah.
So the two example models that you gave before with Brownian motion and this tiling model, I suppose both of them can be interpreted as giving a Navai class of weights.
Yeah, well, they're also varying. We also have varying weights, but you can verify that there is an analog of these limit statements. Like again, you only need some, only need some information in certain blocks, and if these limits in these blocks, they will have same structure, but I have to explain a little bit how these blocks now look like. So,
okay.
But the answer to your question is yes. So this theorem, or actually a variation to this theorem, like the varying case, actually explains the CLT in both these cases. Yes. Now I have to be a little bit careful, because for the lozenge tilings of this hexagon with a little tooth pulled out is actually something that I have not verified, but I'm pretty sure that you can verify it with these methods. But for the Brownian patch, you can do it. Yes. Yeah.
Thank you.
And I think you could even get sort of Gaussian free field with those things also, but we have not done that yet. But I'm confident that it will be possible. Yes, with these methods too. So there's a little bit more about this recurrence. Like we have to go to a matrix J, a recurrence matrix, but you cannot just get it out of the nearest neighbor recurrences. So this is sort of like a next important step, how to do that. So what we do here is, maybe I'll just do it first again for m equals 2, what we need is that we need a family of polynomials, but we need one polynomial of each degree. So for degree 10, we only need one polynomial of degree 10, and for 9, 1. But for the multiple orthogonal polynomials, there are 10 different candidates, or maybe 11, for polynomial of degree 10. So which one? We have to make a choice. So let me draw again this graph. Now, there was one point here. Our ensemble had a particular coefficient, an n1 and an n2, that was given to us, right? Our ensemble says like n1 paths have to end up there and 2 paths have to end up there. So this is something that is given to us. And what we're going to do now is that we're going to choose a family of polynomials, and for each degree 1 by taking an upright path like this. Okay, so what we're going to do is a path pi of coefficients here, and it's 0 to infinity, and kn, the length of kn is going to be n, and each step you go either up or you go to the right. So k minus k, not here, is an element in, well, let's do it general, in one of those canonical base factors. So you go either up or you go to the right, or the other direction if you go in higher dimensions, okay? And you also want this to go to the special point that you have, okay? And then you look at, so in the notation that I had before, there was the bi-orthogonal ensemble. I have two sets of functions. One of the set I choose for j 0 to infinity is exactly this polynomial pkj for j going from 0 to infinity. Okay? So this is exactly what I want to do here. This is what we take. And now I want to go to my Jacobi type matrix, my recurrence matrix, which means that I want the recurrence not between nearest neighbors, but recurrence within this family. Okay, so I mean, remember that I had a recurrence, for example, for this polynomial, and a recurrence that goes with this one and then that one, but also this one. And I'm not allowed to take that one. But I could swap this. I could swap a few. And actually, what I can do is I can swap this one, put it in there, but then I get one here. And then this one, there's this consistency relation. And then I can use this one with that one and put it here. And then there and so on. In the end, I can get a relation between those polynomials.
Maurice, yeah. Could you just explain this choice of phi j in terms of the p? That is not uniquely given, right? You could do many upright paths.
Exactly. Yes.
But there's some invariance. There's path invariance.
Yeah, so this was actually one of the big problems that we had, because yeah, let me come to that exactly. Because what you can do now is you can make a recurrence for these polynomials. Oops. Which means that I can just now use this recurrence here, like a pk0, pk1, and so on. And then here I get a recurrence matrix that is a one-sided bandit. That's why I was sort of emphasizing the one-sided bandit. One-sided bandit matrix. But this recurrence depends on your path P. And your polynomials depend on the path, but also your recurrence matrix depends on P, on the path. So what you now can have is the lemma is what we need to study is basically that if you want to consider a linear statistic, the moment generating function, you get now a determinant, but now it's going to be e to the f it times f times j pi. And here it's jk running from 1 to n. Oh, capital N maybe. And this is a bit surprising if you look in this case. It's because everything depends on the path. And somehow it shouldn't. right? And this actually gave us some problems because now you could try to decompose your fj pi into like a lower triangular and upper triangular part, but this also depends on your path. And actually, if you compute this matrix, it can be computed. For each path, it can be computed, but it's complicated. And this was a huge problem because I mean, you can do this for like, let's say, evenly distributed paths, like half go there, and then you see that there is a pattern. And then you see indeed that you can actually decompose it in lower triangular part. And for some miracle, the commutator is trace class. And if you take the trace, it doesn't really matter on how you take the path. And there are all kinds of miracles happening. So there should be something more invariant. And that's actually indeed how we went, how we solved the problem. So what it turns out is that there is actually GPay. So there is actually a nice operator around here that is actually independent of the path. Okay. And this is something that we did. So I have to define this now. So we take so this is an operator now. T, let me call this a phi. No, let me call this calligraphic T. Curly T, phi, which is an operator that's basically a Toeplitz operator. It's just basically defined in the space of polynomials. And it maps the polynomials to the polynomial part of what? Of f, and I also assume now that f is a polynomial. The test function that I do my linear statistic with is a polynomial, is z plus aj over z minus bj, and this is this new. These are these limits from the Navai class times qc. So f is a polynomial, so this becomes here a rational function. And then I multiply with a polynomial. I have a polynomial part, and that's the one I keep. So it's basically a Toeplitz operator, right? Toeplitz operator is also multiplication by operators, and then you project back on your polynomial space of polynomials again, right? So it's basically the Toeplitz operator with that symbol. And now the point is that actually the path, so this operator is behind the whole story, but the path comes in by the choice of the basis. So what we did then is that we introduced an operator T phi P. This depends on the path. This is the matrix representation of our Toeplitz operator in the basis, which is now the product over z minus bj mu, and then j is running from 1 to say n of k, this is the factor kn, and then the jth entry of that. So I will actually take this j here. So my kn has this, is a vector kn1 to kn m. And this is from J to M. So I will have a space of polynomials, and I take this basis instead of the basis. If you take this Cj as the basis, just the monic polynomials, the monomials as the basis, and look at the matrix representation of T phi, it will be a genuine Toeplitz matrix. But now it's not a Toeplitz matrix because it has this, it's with respect to a different basis. And what you can prove is that your fj pi that you're interested in minus this t phi p around the n entry, this goes to 0. So that's a lemma. That's the first lemma. So the thing is that we really couldn't really compute. I mean, this JP is some complicated matrix. The f of JP is something complicated. We couldn't really compute it, but we could prove that around this entry, the n entry, it looks like the same as this matrix around the n entry. which is also complicated because it's that Toeplitz operator in the weird basis. But the difference of the two is 0. This is what it is. And the fun thing is then that we could prove that this T phi P could be decomposed in a lower and an upper triangular part that is then traced, for which the commutator of these two parts is trace class. So we could write the T phi P into a T phi P plus and a T phi P minus, such that T phi P plus is upper triangular and the T phi P minus is lower triangular, and the T phi P plus, the commutator with the T phi P minus is trace class, or it's actually the trace is actually finite rank if you have polynomials. So actually the trace of this will be exactly equal to the sum of fk, fk, f minus k. It's actually finite rank because we're working with polynomials only. So this is something that we could prove. Now, we do this rather, we don't really have control over these matrices, but we can show that there exists such a thing, and that actually we can compute the limit in the end. But for example, I don't really know what happens with the diagonal terms. If they are here or there, I'm actually not 100% sure. Okay, so one of the nice things from a point of view of multiple orthogonal polynomials, I think, is that like for usual orthogonal polynomials, you have this Toeplitz matrix with a symbol z, az plus b plus a over z, which is sort of a canonical object. Dennis Rachmaninoff says, well, in the end, every Jacobi matrix will look like that, as long as you're on one cut. So for the analog of that should be, I mean, there is this operator should be somehow play a very important role. The operator that I wrote here, this is the operator. And the path is just choosing a different basis, but I mean, traces are independent of the basis. So somehow this is just some, you don't need, this is something that is sort of irrelevant for the final result. Okay, I think that is all I wanted to say.
Okay, let's all thank Maurice.